So we talked about the fact that you have plasma coming down through the afferent arteriole, and some of the fluid in that plasma gets squeezed out here at the glomerulus. And the fraction that gets squeezed out is called the filtration fraction, and so that's the GFR divided by the renal plasma flow. But now what about the solutes, for example sodium? How much sodium gets out here? Well, it turns out that since sodium can easily get out of these capillaries, because it's just one atom, it gets split up exactly the same way that the fluid does, that the water does. So, in other words, if the filtration fraction is 20% or 0.2, that means that 20% of the water coming through this afferent arteriole will get filtered, and also 20% of the sodium coming through this arteriole will get filtered, and the remaining 80% will go back through the efferent arteriole. So to make this really clear, let's say you have 1 liter of fluid coming down through the afferent arteriole. How much of that is going to get filtered, and how much is going to go back through the efferent arteriole? Well, if we said the filtration fraction is 20%, then that means that 200 milliliters will be filtered here at the glomerulus, and the remaining 800 milliliters will go back out through the efferent arteriole. And then let's say that in this 1 liter of water, we had about 3 grams of sodium dissolved. How much of that is going to get filtered here, and how much of that is going to go back out through the efferent arteriole? Well, it works exactly the same way as with the water. So 3 grams coming in, 20% of 3 grams is 0.6 grams, or 600 milligrams, and the rest is going to go back out this way, and that's 2.4 grams. Now, something that's kind of obvious is that the amount that's coming down through the afferent arteriole has to be equal to the amount that's filtered plus the amount that's going back out through the efferent arteriole, because there's simply nowhere else it can go. But sometimes people give this a fancy name, this concept, and they call it mass balance. So if you ever hear this term, you know it's just referring to that simple idea. Now that concept always holds, but the idea that 20% of the stuff coming down the afferent arteriole gets filtered is not always true. So albumin, for example, should have about 0% of it come out through the capillaries because it's too big and charged. So all the albumin coming in should be going out through the efferent arteriole. And then there might be some substances in between sodium and albumin, in the sense that some of it gets out through the glomerular capillaries, but less than 20%. And so that would be true of a substance that has a harder time getting through the 3 layers here, but not quite as hard of a time as albumin. In the very beginning, we said the kidney helps the body get rid of wastes, and it does that by purifying the blood. And some of those wastes were urea, for example, which is a byproduct of breaking down proteins. And there's also uric acid, which is a byproduct of breaking down DNA or RNA. And so now that we know a little more about the glomerulus, let's think about how these things get excreted. So let's talk about urea. And let's say that urea maybe has a 10 milligram per deciliter concentration in the plasma. And so a deciliter is 1/10 of a liter, so that's the same as 100 milligrams per liter. And let's say that you have a GFR of 100 milliliters per minute, just to use nice round numbers. If urea has no problem here getting through the 3 layers of these capillaries, then how much urea is going to be filtered per minute? And this ends up actually being quite easy to calculate. And the reason is that the concentration of urea out here is actually going to be equal to the concentration of urea here. The reason why that is you have some amount of urea here, and that's being carried in some amount of fluid that's coming down through the afferent arteriole. And then the amount of fluid that gets filtered here at the glomerulus is defined as the filtration fraction times the amount of fluid that was coming down through there. And we said that for a substance that easily gets through these capillaries, it's the same fraction that gets out. And so in that case, the amount of urea that gets through is the filtration fraction times the amount of urea coming in. And then we just noticed that the concentration of urea out here is simply the amount of urea coming in divided by the amount of volume coming in. And the concentration of urea here is the amount of urea being filtered divided by the amount of fluid being filtered. And if we're dividing, these two things cancel, and so we see that the concentration here is the same as the concentration there. So that was a bunch of math that honestly may have been unnecessary, but the point is just to realize that for something that's freely filtered, that gets easily filtered, its concentration will be the same in Bowman's space as its concentration in the afferent arteriole. And therefore the amount of that thing that's going to be filtered here at the glomerulus is just going to be equal to the concentration of that solute, in this case urea, times the glomerular filtration rate. Because the GFR tells you the amount of volume that's getting filtered, and since the concentration of this thing is going to be the same in Bowman's space and in the afferent arteriole, you just multiply the volume times the concentration to get the total amount. So in this case, it would be 100 milligrams per liter times 0.1 liters per minute, because 100 milliliters is 0.1 liters. And so that will give you 10 milligrams per minute. So this is how much urea is getting filtered every minute.